genius. So he has drawn a picture for each of the voltages and currents. And he's been right. What that would mean? Well, let's say that we first know, for example, the voltages, the time domain voltages that come into the nonlinear part. Well, that means that I can start with the nonlinear analysis knowing all voltages at any time as the input. I can start solving differential equations step by step in time. I will have to do it for several periods of the signal due to the fact that some of the nonlinear capacities or nonlinear inductors would have to charge only. But after I do that, I will get a periodic behavior here in the nonlinear part. Once I will observe a periodic behavior in the nonlinear part, I would also know the currents over here. So if there are some voltages, I will also get the currents that flow inside the circuit here. I will know those currents as samples in time. Now I can use Fourier transform to get those currents transformed to the frequency domain. So I do it. And I have frequency components of all currents at those wires or terminals. This is a linear circuit. I know the currents on all of the terminals or ports, and I can run an analysis of this N port and get out some kind of parameters, be it Y parameters, be it S scattering parameters. Anyway, this analysis would give me at each frequency components of the voltages. So I have currents at the input, I get voltages. Still, I will get for each voltage, for example V1, I will get frequency components, that is DC part, frequency component magnitudes, and phase shifts. Once I have this, I can feed it forward to the inverse Fourier transform and get time samples of the voltage. Now I have begun with some time samples of the voltage for each connecting wire, and I have run through the process and got back some time samples of voltages. Remember, I told you at the beginning we have an ingenious engineer who has just watched the schematics and said, okay, this would be the time domain behavior of the voltage 1, voltage 2, voltage 3. So he was ingenious. So do you possibly know that he has suggested proper voltages so that after the whole process we have got the same time domain sets of samples. And this is called harmonic balance, because you run the whole simulation and you get the same at the output you had at the input. So at this moment we know that we have proper content of harmonics of the signal. Or you can say we have proper time domain shape of any of those signals. That's equivalent. One is in the time domain, the other is in frequency domain, and we have connecting fast Fourier transform or reverse fast Fourier transform. Well, if we had that ingenious engineer, we would have that in one time step. Well, if he was so ingenious, he would not need any analysis because he would know. Unfortunately, mostly we do not have those ingenious people, and we have to somehow manage without them. So what we had a set of time domain samples, or we could say, okay, we have a set of harmonic components. We put it into this process and we get something else. Okay, so in fact, we have an optimization problem. We have to tweak the inputs as long as the outputs from this feedback loop are identical to the inputs. At that moment, we have harmonic balance. We have balanced both parts of the circuits, the linear part and the nonlinear part. And this is the method. Now there is a number of tricks. The first idea you would possibly have is I have tried to put here 1 volt, and after the loop 2 volts came out. Well, what about trying to put there the average 1.5 volt? Now, yes, this would be possibly easier at the harmonic side, so you can start the process here or there. What you want to achieve is the harmonic balance. That is, you test some input, run it through the chain, and get the same input after the process. And the process consists of time domain simulation of the nonlinear part. The time domain simulation must run at least as long as the, let's say, initial effects, transient effects are gone, and it must cover at least 1 full time period of the basic frequency component. After running this analysis, I can transform the solution to frequency domain, put it through the linear circuit. I have some resulting behavior in frequency domain. I transform it, and I must get what I have started with. So the full loop must be in balance. All harmonic components must be so balanced that the voltages in time domain and the voltages in frequency domain are balanced. Now I will ask you for questions, and then I will make a few comments. So please, your questions now. No questions so far, so I will start with commenting. This method is quite efficient. I mean, it's tricky to program all those things around, but finally the algorithm is efficient, but has some bottlenecks. First, most of the bottlenecks come out from the behavior of Fourier transform, of that something in between those 2 sheets of paper. The first is, I must be absolutely sure that the nonlinear part does not produce some significant amount of frequencies or frequency components that are not considered here. Because in order to run the whole thing, I have to somehow decide that I will, for example, use 16 harmonics. That means I will have 32 time domain samples. That would be 16 harmonics. Now, what if there is an important harmonics at 18 times the basic frequency? Well, if this is the true, remember I will get it mirrored inside, and it would pretend a much stronger 14th harmonic and distort its phase, which then would prevent me from reaching harmonic balance at all. So I have to have a good estimate for the harmonic components in order to have enough samples and to keep sampling theorem. That's the first point. Given the nonlinearities of the elements, you could somehow guess a correct number of harmonics. So fine. It will be a nice idea for analysis of nonlinear amplifiers where you have clearly a single frequency at the input and you try to get harmonic distortion, that is mostly the third harmonics at the output, or the ratio of first and third harmonic at the output. That's simple. What would be less simple is designing an oscillator, because the oscillation itself could tune some nonlinear capacities or inductors within the design. I mean, if you have, for example, a field effect transistor, the first model of that is the gate to source capacitance. Then you have the voltage over it driving a current source, and you have the drain capacitance. Now for small signals, this is a nice linear model. Once you increase the signal, both the transconductance would be nonlinear and those capacities become to behave nonlinearly. At low frequencies, the transistor does not contain a significant amount of energy inside. I mean, the capacities are much lower than the capacitors and inductors defining the frequency of an oscillator, for example, a Colpitts oscillator. The main tuning parameters are outside of the transistor. But at high frequencies, the capacity of that, be it close to 1 picofarad, might be important. And now, with increasing signal swing, you will get a nonlinear capacity that will, in fact, change the tuning of the circuit. So you start at some build-up condition, and as the signal builds up and increases the magnitude, it happens that the signal changes the capacity and therefore detunes the oscillator, and therefore the whole frequency is shifted a little bit. And now the ugly story of Fourier transform comes here. We have a signal with some period, but as the frequency has shifted, we sampled it incorrectly, so that we are sampling a signal whose frequency we do not know exactly, whose basic frequency or whose period we do not know, because it's a result of the nonlinear analysis we have still not carried out. And then the process, the Fourier transform that connects both sides, might become unreliable. This might be a problem especially in the case you have more nonlinear elements. I have a story about that. Some time ago we have got for free some 20 installations of leading software for nonlinear analysis of microwave circuits, and we use it in our department. But then I have been investigating a special oscillator based on a distributed amplifier, which has 4 transistors inside, but all of them are somehow exactly affecting the frequency of oscillation. And the simulator was working using harmonic balance, and this uncertainty in the correct frequency that would result from the oscillations has caused the numeric solver to be unstable. That is, we got no results, to be fair. So I asked the user support. You know the story. First they try to convince you that you are completely dumb and you do not know how to switch on the computer. So I called directly to the center in the United States. We have been working about that. They learned that I understand what I'm doing, and then I have got a nice reply. I had 2 questions. Will this feature to solve this particle circuit, I hand you with this question, be included in a future version of your software, and will it be the next version? And there was a nice reply: yes, it will be included in future versions, but it will not be the next one. And this reply is valid for 20 years at the moment. So harmonic balance is a very nice method which shortens the time necessary for simulation by an order of magnitude. So it's very handy for circuits where you exactly know the frequency and it does not depend on the nonlinearity very much. Once this is not the true, you might have crazy solutions or no solution at all. So harmonic balance, an extremely efficient method for amplifiers, mixers, frequency multipliers, might have some problems with oscillators. Now, again, time for your questions. Well, we have spent some time in lecturing. Both you and me deserve a 5 minutes break. Then another question on your questions would follow. 5 minutes break.